Now, there are many different types of enthalpy values. There is not just enthalpy for solids. There's also enthalpy for liquids and for different kinds of changes. So let's list a couple of different ones that are relevant to this field. So there are many types of enthalpy. And we're only going to be talking about a few of them in this chapter. But if you go into physical chemistry, you will continue to learn more. So there's delta HC for combustion. There is delta HF, enthalpy of formation. There is delta H lattice, which is the lattice enthalpy. There is delta H vap, which is for vaporization of a liquid into a gas. And there's another one of those for every different type of phase change. There are many of them. We are going to focus on enthalpy of formation for a little bit longer. So enthalpy of formation, this one has a more specific definition. This one is the enthalpy for reaction in which exactly 1 mole of a pure substance is formed from free elements in standard states. Okay, that's a long definition. Let's break it down into the important parts here. So this is the first important part. 1 mole of a pure substance. So that means if I'm talking about the enthalpy of formation of a particular compound, there needs to be only that one compound formed, not several, just one. And the coefficient in front of it needs to be 1. So 1 mole of one thing is the only item on the product side. Here's the other interesting part. Free elements in standard states. So that means for a formation reaction, all of the reactants need to be single element compounds, and they need to be in their standard state. So what is a standard state, you say? It is going to be the most stable state under standard conditions, STP. You are going to find there are a lot of gases and a lot of solids at standard conditions, and there are not a lot of liquids. Let's show a couple of examples. So here's an example from the last problem that we did. Nitrogen plus oxygen goes to nitrogen dioxide. And that delta H of formation, 33.2. So you can see here the standard state of each of these is a gas. You can see that there's only 1 mole of one product formed here, and that each of the reactants only contains 1 element in each compound. Okay, let's do another one. 2 carbon, specifically graphite, plus 3 hydrogen, dihydrogen, plus half a dioxygen will form ethanol. Liquid, and that delta H of formation doesn't fit on that line. It is negative 277. So here, carbon, the standard state at standard conditions, exists as a solid, but because there's more than one type of solid that carbon could be, it could be graphite or graphene or carbon or coal, we specify graphite. Hydrogen is a gas, oxygen is a gas, and ethanol is a liquid at room temperature. Let's add a note here. Multiple solid states exist for this compound. And also note, your delta F or delta H can be positive endothermic or negative exothermic. So I know what you're thinking. How am I supposed to know what the standard state of a particular compound is? I've only had 1 year of chemistry. I'm no expert. My advice to you is, if you see a compound that's made mostly of non-metals, something on the right side of the periodic table, it's probably going to be a gas at STP. If you see something that is made of a metal, something more on the left side of the periodic table, it is probably going to be a solid at STP. There are not very many liquids at STPs, at least not for elemental compounds. And if you don't know, solid would be a great guess. Okay, and one more example, the delta H of formation for oxygen is going to be 0. And that's because oxygen is a free element in its standard state. And that makes sense because the rule was enthalpy of formation has to have 1 mole of one product, and it has to be formed from free elements in standard states. Oxygen already is a free element in its standard state, so you can't form it from anything else. This is the most you can reduce it, so that means its enthalpy of formation and standard conditions will be 0. So anytime you have an elemental compound in its standard state, the enthalpy is going to be 0. Okay, so now let's see how we can use those. So all of these standard delta H values of formation can be found in reference tables, and we can use them to compute values we don't know. Standard delta H of formation, just delta H of products not in the table. Sometimes a compound is too difficult to measure, and if you want to measure it, then you can measure it by taking the sum or the difference of other compounds. And we are going to switch pens. Okay, so if you think about it, when you are making some sort of a compound and you're not making it out of elements, you're making it out of some sort of normal multi-element compounds, the process should look like reactants broken down into their elemental groups, like these, and then reformed into the new compound. So if you wanted to find the delta H of the reaction, you could take all of the values of the products delta H of formation that it takes to form those products from their elemental compounds, and you can subtract out the delta H of formation for the reactants, because the reactants are being unformed, deformed, backwards formed, whatever you want to call it. So you have to unform the reactants and then form those into products. So we subtract out reactants and add together products to get the total delta H of some sort of a reaction using the values from this table. And these numbers right here, these n's, these are the stoichiometric coefficients from your reaction. Because the delta H of formation values from the table are only for 1 mole of a particular compound. So if you're trying to find more than 1 mole, you're trying to make more than 1 mole, you need to multiply it by the stoichiometric value according to rule number 1 on the previous page. Okay, so let's see if we can test out what that looks like. So here's a compound, ethane, C2H6, which is a gas at STP. And there's delta HC, and that's combustion. So we're trying to find the delta H of this particular reaction, and we're going to try and do products minus reactants. So the first thing we need to know is, what are the products and the reactants? We weren't given an equation, a chemical equation for this problem. This is some of that 115 information. We should know that whenever you have a combustion reaction, you are burning some item in oxygen, and you are forming carbon dioxide and water. Always, always, every time combustion. So we're burning something, C2H6, which is a gas. We're going to be burning it in the presence of some amount of oxygen. And we know we will always form carbon dioxide as a gas and water as a liquid. So that's a good start, but something is wrong with this equation. This equation is not balanced. Good news, we are not first-time chemistry students. This is within our range of abilities. So let's have a throwback and practice balancing this equation. So I'm going to identify this as an elemental compound. Elemental compounds are great to leave for last when balancing. So I'm going to cover that with my finger. So there's 2 carbons on this side, and I want to have 2 carbons on this side. So I'll put a 2 in front of carbon dioxide. There are 6 hydrogens on this side. I would like to have 6 hydrogens on this side. So we'll put a 3 in front of that. 3 times 2 is 6. And now all that's left is the oxygen. There are 1, 2, 3, 4 oxygens here, and 3 oxygens here is 7. And now I'll uncover my elemental compound. There are 2 oxygens here. So we need to multiply 2 by something to get 7. I'm going to multiply it by a fraction, 7 over 2. Not beautiful, but it works. Okay, so now that I have a balanced reaction, now I can do product minus reactants of the enthalpy of formation values to find the enthalpy of combustion of this reactant. Let's see here. So the delta H of this particular reaction, we're going to write it in symbols first to make sure we don't forget anything. So the first product is carbon dioxide. We're going to have 2 times the delta H standard of formation of carbon dioxide gas. The state is important because there might be carbon dioxide liquid as well. Then we're going to have 3 times water. Delta H standard of formation of water liquid. Those are my products. Then we're going to subtract the reactants. So 1 times ethane. Delta H standard formation of ethane as a gas plus 7/2 times oxygen. See if I can fit it here. Delta H formation standard O2 gas. Just barely. Okay. So now we have our plan. So now we're going to go to the reference table at the back of the textbook and look up the numbers that we need. So we're going to have 2 times the number here for carbon dioxide, which is negative 393.5. And these numbers have units of kilojoules per mole. And this is going to be 2 moles. So 2 moles times this many kilojoules per mole is just going to give us kilojoules. We want to do the same for all of them, but I'm going to be lazy because I did it for the first one. Negative 285.8 for water minus 1 times the value for ethane, which is negative 84.7 minus 7/2 times the value for oxygen. And remember we said for elemental compounds in their free and their standard state, the delta H of formation is 0. So times 0. And if we use our handy dandy calculator, we add those together, we should arrive at negative 1,560 kilojoules. So using values that we knew for formation of these different compounds and multiplying them by their coefficients, we were able to find the enthalpy of reaction for a reaction we didn't have the value for. So this has been quite a lot of math, but you are now able to use thermochemistry to find heat capacity, enthalpy, internal energy, and work. That is the end of the thermochemistry chapter.